Hello everyone, welcome back to the channel. In this video, we will be discussing about the last problem of today's weekly contest, find k sum of an array. The problem states that you are given a positive, you're given an integer array nums and a positive integer k. You need to find out the kth largest subsequent sum of the given array num. Okay, for example, if this is the given array nums 2 4 minus 2, you will first find out all the subsequences, and for each subsequences you will calculate their sum. Okay, so there are total 8 possible subsequences, right? Because there are 3 elements, so 2 to the power 3 is 8, so there are total 8 possible subsequences, and if you calculate the sum of all those subsequences you will get these values. And now once you sort this, you have to return the fifth largest among these values, so answer would be 2. So the problem is straightforward. Now before jumping to the solution, I would like to emphasize that this is a little bit tricky problem, and I have tried my best to dissect it and into smaller pieces so that we all can understand easily. And coincidentally, this is the 100th video in this channel, or I am solving the 100th question on LeetCode live, and I was not able to do this during the live contest. So this is just a coincidence. Now coming back to the video, again, I am sure if you stick to the video till the very end, you will understand each piece of the problem. So let's start. We need to find the kth largest subsequence, right? So instead of finding out kth largest subsequence, first let's assume that the array contains only positive integers. We will remove this constant later on because the original question contains negative integers as well. But for now, let's assume that array contains only positive integers, and we need to find out kth smallest. Why smallest? Because smallest is easier to understand. Once we understand the entire solution, we will modify like this solution to work for the original problem. So for now, only positive integers, and we need to find out kth smallest. So let's assume that there is only three elements in the array, 1 2 and 3. So now you can like you we already discussed that we can't iterate over all the subsequences, right? Because total number of subsequences are 2 to the power of n, and the value of n is 10 to the power 5. So 2 to the power of 10 to the power 5 is humongous, and we can't actually enumerate all the subsequences. So hence we need to do something better. Now one observation that you can make from the problem is the value of k is something small, right? So you can guess, or you can think of the way that you only need to find case numbers or case numbers from the beginning, because we are finding out case smallest, right? So we only need to find out kth number from the beginning, and if we are able to do that efficiently, we have solved the problem. So instead of iterate, like we can't enumerate all of them, so what we will do, we will use a simple trick. We'll say that okay, we'll maintain a pair of sum comma I. Sum denotes the current subsequent sum, and I denotes the index that we need to visit next. So initially subsequent sum is 0, we haven't considered anything, and the next index that we have to visit is 0 as well. So that this is 0th index, 1 index, 2 index, right? So the next index that we need to visit is 0 as well. So as we have already applied the constant that our array will contain positive integers, so the first of the subsequence among the, like we need to find out the first k, right? So the first element in this k array list is 0, because 0 is the subsequent sum when you don't take anything, and that is the smallest, right? Because every number here is positive. So the initial number is 0, and the first index that we need to visit is also 0, because we have to consider the first index. So for now we are at this state, and we have said that we subsequent sum is 0 and the first index that we will be visiting is 0. Now we have two choices. We have to consider 0. Either we will take 0 or we will not take 0. If you take 0, the updated subsequent sum would become 1 comma 1, and if you don't take 0, updated subsequent sum would remain 0, and the next index that you have to visit will become 1 because you have decided what to do with 0th index. So now you have to decide what to do with first index, right? So till now we have visited these, like from this state we have covered these two. So we have already taken this 0, sorry, we have already taken this 0 into consideration. Okay, now we got two new elements, 0 comma 1 and 1 comma 1. Now which one of this will you expand first? Remember, you can't expand everything, otherwise you will end up in 2 to the power of n solution, right? So you have to expand wisely. Now which one of 0 comma 1 and 1 comma 1 will you expand? The answer is 1, 0 comma 1, because it says that you have to evaluate starting from index 1, right? That's the uh, second integer 1, that says that you have to evaluate starting from index 1. And first integer says that current subsequent sum is already 0, and and here it says that current subsequent sum is already 1. Now if you expand this, this one will be considered in every other subsequence that you will consider, and this 0 will be considered in every other subsequence that you will visit after this. So which one of these which should will give you smaller values? This one, right? Because this one has already smaller subsequent sum and the indexes are same, so this one should give us smaller subsequent sum, because whatever you will get after this is same. So currently whoever has smaller subsequent sum has the chances of giving you smaller subsequent sum. So you will expand this. Now because you are expanding this, see that can you consider this 0 again? Like can I make another 0 here? The answer is no, because this 0 and this 0 is exactly similar. So what is this 0? You haven't taken anything. And what is this 0? You haven't taken anything yet. So these two 0 are exactly similar. Hence, we will not consider this 0 in our set, and we will just expand this. Now, if we expand this, again, there are two choices. Either we take that first index or we don't take the first index. So if you take the first index, the value that will be added to your subsequent sum is 2. So the new sum would become 2, and you will now consider everything starting from the next index, which is 2. Okay, now similarly, if you haven't taken that, the value will remain 0, and the next thing that you have to visit is 2. So for now what you have done is you have already expanded this and you have already expanded this. Now you have these three nodes into consideration. Now which one you will expand now? Again, the one this which have the smallest value, that has the potential to give you smaller values. So again, we will, instead of expanding this, we will expand this one. And before expanding, can we put this 0 in our set? The answer is no, because this is again exactly similar to this 0, which says that there is nothing in our set yet. So there is nothing in our set yet. So now again we will expand this node. Again we have two choices: either we take this or we don't take this. Okay, let me consistent. So we take this or we don't take this. So if we don't take this, we will end at 0 3. If we take this, we will end at 3 comma 3. So what, like why 3 comma 3? Because the index 2 has value 3. So again you have already like expanding this particular node and you get these two nodes. Now which one you will expand? There are four nodes. Again you will try to expand 0, but there is no other node after it, right? Like after 3 there is no other index, so it can't be expanded further. So this is also done. Now you have three nodes. Which one you will expand? This one, because this has the smallest sum, so this has potential to give you smaller values. Now once you consider this you can add to your set. Why? Because this is a unique combination that you have got. So currently you have considered only one combination, whereas you have nothing in your set. Now you have considered something, like this one actually denotes that you have considered the first index. This one you will add to your uh, kth list, and for now assume that k equals to 4. So we need to find out the four largest values. Okay, so we need more too. So I am doing all this so that we understand what we are doing, and we will optimize it further. So now we expand this particular node. Okay, now if you expand this again, you will get these two nodes, one which have value, or for now let's assume that k is 3. Okay, so you need one more node, one more value here. So now you we expand this. Either take the first index, or we don't take the first index. So if we take the first index, the value is 2, so 1 plus 2 would be 3, and if we don't take, the value will remain 1. Now again, which one, like this is done, right? You have visited, or you have expanded this particular node, so this is done. Now which one you will expand out of these 1 2 3 4? We will expand this one because this has the smallest value. Again, let's expand this. Now can you add this one in your set? Answer is no, because this one and this one is exactly similar. You haven't taken anything extra here, right? So this one and this one is exactly similar. So you can't take actually this one, but let's expand this. And if you expand again, there are two choices: either you will take this, or you will not take this. If you take this, you will get 4, 1 plus 3 4, and if you don't take this, you will get 1. Now again, which you have explored this particular node. Now you have explored this. Now you have left these nodes. Which one you will visit? We will visit the one which have smallest value, which is 1. Now because there is no other thing, we can't take this one as well, because this one and this one is exactly similar. So we can't take this, and we can't visit further as well. So now which one to visit? These two, right? Now this two is something that we can add. The reason being, these two is this different from any of the values 0 and 1, or any of the combination that 0 and 1 covers. So once we get 2 into our answer, we don't need to expand further, because we are asking for three numbers, or the three smallest number, and we got three smallest number in our list. So now we'll stop the algorithm here and see we haven't visited all the nodes. So this is a smaller tree, so that's where you might feel that we have visited most of it. But as and when you expand, you will notice that you are not you are saving a lot of iterations. So that's how we will get the list. Now if you implement this algorithm, like what would be the, like we will discuss the time complexity as well, but what would be the approach? Because we need to find out the maximum values or minimum values, right? We need to we need some kind of sorted data structure, and we are popping out the first element or the minimum value among all this. So this actually is a mean heap that actually does this, like popping an element efficiently and inserting the element and removing the first element. So this is something that mean heap does, and mean heap is equals to priority queue, right? So we'll maintain a mean heap, like small to large priority queue. Now until the size of the priority queue is less than k, what we are doing, we are popping an element from the queue. Initially priority queue will contain 0 0, and we are also maintaining a three things. Like we have currently maintained two things, but we have been checking before adding that whether it is unique or not, right? So that's what the third value denotes, that whether it is unique or not. Now if it is unique, we will add it to our top k elements, like the k lists. And then what we will do, we will consider the current index or the next index. Now there are two choices: either you take the next index, or you don't take the next index. So if you take the next index, the sum would become sum plus array of next index. Okay, and because you have taken this is a unique combination now, because this index hasn't been taken before, and you are taking this first time. So this is surely a unique combination, because currently whatever was there is already unique. Like whatever was there, you are adding one more, like you are adding the next element to it. So this is definitely unique. So you are marking this is unique as true, and just incrementing the index, just like before. Now the next is, you can actually ignore the current index, so the sum will remain sum, index would be incremented, and this would not be unique, because whatever sum was there, you have just copied that, and you have decided not to take the current index. So whatever you have taken before is actually the current values. So this is false. So that's how we are maintaining, like after we implement this and this while loop is over, this we will get like this top k array will contain k smallest elements. So hope this point makes sense. Now what is the time complexity? Time complexity is smaller than 2 to the power of n, but uh, sadly it is not efficient. It is not in order in polynomial time. It is still exponential. The reason being, we are visiting lot of nodes. See, we have visited 0 comma 1, but we haven't taken this 0 in our set. Similarly, we have visited 0 comma 2, but we haven't taken 0 in our set. We visited 0 comma 3, we haven't taken 0 in our set. Similarly, we visited 1 comma 2, 1 comma 3, we haven't taken them in our set. So we are visiting lot of nodes to just add k elements. So it is still in exponential, but faster than order of 2 to the power n. But this also will not solve the problem. So in a way, why it is not solving, just to emphasize, zero, like let's take the, let's we have three elements, right? So let's just maintain three binaries, 0 or 1. So if everything is 0, it means nothing is there. If let's say 0 1 0, it means 2 is there in our set. Okay, so this three things denote exactly the same element, right? These three things denote exactly the same element. Similarly, these three things denote exactly the same element. And similarly, these two things denote exactly the same elements, right? Now, because you will be iterating over all of these, and that's where the complexity is not polynomial, instead it is exponential. The reason is, you are not adding top to top k every time, you are only adding if it is unique, right? We somehow, if we are able to remove this if condition, and some if we say that okay, we can find an algorithm where we always push to our queue, or sorry, always push to our array top k, then this entire thing would take exactly k iteration, right? And the complexity would be k into log of n, or log of something, which is either n or something. So that would be the time complexity if we are able to remove this if condition from here. So in a way, what we need to do, we need to skip iterating over non-unique pieces. So previously this issue was there because we are iterating over non-unique pieces as well. That's where we need to maintain this is unique, right? So we need to skip iterating over non-unique pieces now. So now the problem is just we need to find out a way to just like we will apply the same algorithm, exact same algorithm, just that instead of pushing non unique elements, we will only push unique elements. Now we are only pushing unique elements, this if condition will not be required. And hence, this entire loop would end in order k time, like only take exactly k iterations, and hence the complexity would be k into log of something. So something will look at what is something is, but why log? Because we are using priority queue here. Now, hope this point makes sense. Okay. Now we need to find out uh, how to make sure that we are iterating over unique elements always. So for that, we can just make an observation. Uh, why, like if you look at what all non-unique elements you are iterating over. So let's just move it to the next pages. So okay, now let's come back here, move it down. So now if you look at what all non-unique things you are iterating over, non-unique thing only comes when you have zeros at the end, right? See, when you have zeros at the end, then only non-unique things comes out, right? So in a way, if you avoid appending zero, what is zero? Zero is you are not taking an element. If you avoid that particular piece and still ensure that you are visiting almost both the cases, then you can easily skip non-unique elements. So in a way, we need to do only one thing. We need to skip iterating over, or we need to skip elements. At every chance we will take both the elements, we will take elements, we will not, there will not be any case where we are not taking any elements. So let's try to find out now. Because we are removing zeros, like we are in a mission to remove zeros, we will not start with zero, right? We will assume that zero is already with us. What is zero? Zero is there is nothing in the subsequence. Subsequence is empty. So we will assume that 0 is always with us. So this 0 will disregard. Now we will start with 1. What is 1? 1 is again, we are taking the first element always. Like there are, let's say, 3 elements. We are always taking the first element. That is 1. Now, if you think, if you are always taking first element, then if second element come, you will not be able to make a case of 0 1, right? What is 0 1? You are not taking first element, but you are taking second element. Similarly, you will not be able to make a case of 0 0 1. What is 0 0 1? You are not taking the first and second element, but you are taking the third element. So if you are completely ignoring 0 here, you will not be able to make most of the cases. So what instead we will do, remember that we have 1 at the end, right? Now we know that we have intentionally skipped 0, right? So what we will do at the next iteration, we will by ourselves consider 0. So we know that everything is 1 and we have intentionally skipped 0. So in the next iteration, we are considering the second element. Now while considering second element, we will intentionally assume 0 in every of the places in the previous iteration. So for example, here we have 1. So when we iterate, we will iterate over two elements for 1. One is 0 1 and second is 1 1. Basically, you are iterating over both 0 and 1 for the first piece, and for the second piece you are taking the second piece always, because again you don't want to add a case where you are not taking anything, otherwise there will be zeros at the end. So now let's just move forward, it will be more clear. So now again what you have done is you have taken, you have taken the second element, but you haven't taken any case where second element is not there. So for every such cases, if you end up expanding this particular piece, right? If you end up expanding this particular piece, you will be expanding it and adding, considering 0 here. So we haven't considered 0 here intentionally to keep the previous iteration smaller. So here we will expand this intentionally to say that this 0 1 is equals to 0 1 and 0 0. This 0 1 is equals to 0 0 and 0 1. We will consider 0 at the end. And for 3 we are always considering it. Like there is no other choice for the last element. Last element should always be considered, because that's what we have said. If we are not considering, we are actually giving invitation for non-unique elements. So we have to consider the last element always. So that's where we last element will always be 1. Now for the second last element, we will either take it or not take it. So we are sure that the last element of the second last layer of the will always be 1, because we have made the situation in that case. So while considering any of the element of the previous layer, you will automatically break into two parts. So for 0 1 you will automatically break into 0 0 and 0 1. Similarly for 1 1 you will automatically break into 0 1 1 0 and 1 1. Now what you are gaining from here, you are gaining everything, like you are sure that you will be considering everything, yet you are not visiting the non-unique elements. Hope this makes sense. Let's just make one more iteration forward. So now if you take one more iteration forward, you will again say that, okay, I have not taken, I have skipped the not taken case intentionally in the last layer. So if there is a chance that we need to expand anything here, I will take both the case of taken and not taken, because that, I have intentionally skipped the not taken cases. So here we will again iterate over 0 0 0 and 0 0 1, and last element will be 1. Similarly for 0 1 1, we'll iterate over 0 1 0 and 0 1 1, 0 1 0 and 0 1 1. For 1 0 1 again, 1 0 0 and 1 0 1. Why? Because again, just to reiterate, we have intentionally skipped the case where last element was not taken to just avoid this non-unique elements. So with this logic, what we have achieved, what that every time we need to expand, we will be taking the last element, and for the previous layer, like whatever we are expanding, let's say we are expanding 0 1. So whatever we are expanding, we will automatically consider that the last element is not like last element cannot be considered as well. So we are 100% sure that last element would be 1 because we have intentionally skipped the 0 cases. So last element would be 1. So every time we expand a node, we will treat that node as two pieces, one where the last element is 1, the actual node, and one where the last element is 0. So with this, we whatever we are visiting is always unique. So we have solved this particular piece, and we don't need unique at all in our data structure. And if there is no unique, this condition would not be there. And if this condition is not there, we will always push one element in a single iteration, and we have to only find k elements. So after k iteration, this loop will not be satisfied, and we will break out, and final complexity would be k into log of n. So just to make things, like just to reiterate over the entire piece again, what we have said is we can't iterate over every subsequence because number of sequences are very large. So what we have done, we have started with something called sum comma I. We have said that we will try to, like, we will follow the same approach which we should have followed if we have finded out all the subsequences, but we will visit the nodes wisely. So some nodes can be visited, some nodes can't be visited. So for that, we started with sum comma I, which is 0 comma 0, and then we are visiting like nodes which is which has the smallest sum. Now we have seen that we are visiting the nodes which have non-unique values as well. Like, but by non-unique values we mean that same set of values are considered, like 1 2 is exactly equals to 1 1, because here we haven't considered the second element, and so this 1 2 actually contains only one element, which is the first element, and this 1 1 is also containing the only one element, which is the first element. So this subset and this subset is exactly equal, and we have already considered this subset once, so we will not consider this. So what we have seen, that we are visiting one subset more than once in this particular approach. That's where we thought of, if we can find out something, if we can devise out some algorithm that will help us not visit non-unique elements, our algorithm can be a lot faster. So that's where what we have thought is, instead of taking, we will not take 0 explicitly in any of the cases. So we will skip these 0 pieces at all. And when we are expanding, let's say we are expanding this particular node. Okay. Now once you are expanding, while expanding, you will take the 0 cases, right? Before expanding, you will not take, because if you take, you will end up in lot of unused nodes. So that's where before expanding, you will, like, if you are sure that you will be expanding this node, then only you will consider the 0 cases as well for the next iteration. And that way you have founded out a way to skip the non-unique, to skip iterating over the non-unique elements, and that's how you have optimized the solution, that while loop. So let's just quickly look at the code. uh, let's first look at the unique part, like what where we have. So first of all, skip this entire piece is, uh, we remember we have to find out kth largest, but whatever we have discussed till now is kth smallest. So just skip this part, we will come to this part later. For now, this part is interesting. So what we have said is, we need to find out the kth smallest for this nums, and we have already made this nums array all positive. How how and why we'll look at, but this nums array is all positive. Now this is exactly what we have just solved. So what we will do, we will just maintain a node which has three things: sum, index, and is duplicate, which is similar to is unique in our algorithm. So initially we'll put 0 0 and false. Is duplicate is false, right? Because first 0 is not duplicate. Now while there is, like, top k dot size is less than k, we will pop the smallest element, And if it is not duplicate, we will push it to the top k, otherwise we will not push it. Now if the index that we are visiting is actually a valid index, then we will either consider that index. So if we consider that index, this will be the new sum, and either we will not consider that index. So if we consider that index, this is completely new subset, and that's where we have marked is duplicate as false. So this is not is unique, this is duplicate, so that's where it is false. And this is not completely unique, because what we have said is we haven't taken anything, so whatever this sum was there is from the before, right? So that's where we have marked this as true. Basically this is a duplicate. So after this while loop ends, we will have top k will have the top key elements, and that's what we are returning. Why like this, what is maximum, we will again come to that later. But this is how we are calculating top k. Now this will give you TLE, as the complexity is slightly better than order 2 to the power of n, but it is still exponential. So that's where what we have suggested is we will remove this variable, and this variable, if it's removed, this if condition will be removed, and we will improve the complexity. So let's look at this code, this particular piece of code. Again, this is exactly similar to previous piece. Now here, one thing to notice, as we have discussed, we will not consider zero, the the cases where which ends with zero. That is, we will not consider the subsequence which has nothing. So that's where we have initialized this with zero. Previously this was not the case. Now again, this initialization is little bit different. We have taken the first element. If you look at the previous one, we have initialized it with 0 0. That is, subsequence is 0, we haven't taken anything, and the next index to consider is 0. But because we are saying that the last piece can't be 0, so the last piece can't be 0 at all. So last piece should be 1 everywhere to skip the unique, to maintain the uniqueness. So that's where we have taken 0 in the first place, and then we have included, we are starting from nums of 0 comma 1. That is, we are taking the first element, and we the next element to consider is 1. That is, we are starting from this one. Now again, this while loop, we will pull or pop the smallest and push back to the top k, because this is unique, we are sure about it. Now while pushing, we will push, like we are expanding this node, right? So as we have seen that whenever we are expanding, let's say we are expanding this node, so whenever we are expanding, we will consider two cases for a single node. One where this index was not there, that is 100, and where this index was there, is 101. So that's what exactly we are doing. We are This is the previous sum. Now this is the first case where we are not modifying the previous sum. That is, we are considering 101. This part is considered. We are not modifying the previous sum. Previous sum is 101. So 101 we have taken, and we are adding the current element. So we are adding current element and just incrementing the index. Now second case is we will remove the previous sum, because we are sure that it will be 1 at the end, right? So we want 100. So what we need to do is we need to remove the previous sum. Like this one actually denotes that you are taking the third element. So you will remove the previous sum and add the current sum. So in a way, you have made the previous index as 0 and current index as 1. It is exactly similar to what we have just discussed, 100 and 101, and just incrementing the index. So with this, you don't have a unique, uh, like we have get rid of unique, and in every iteration we will be pushing one element to this top k vector, and hence this will take exactly k iteration, and the complexity would reduce to k log n from a exponential time complexity. So hope this entire piece makes sense. Now only thing that remains is we have currently found out the kth smallest value, but in the problem we have given that kth largest. So there are multiple ways to modify kth largest to kth smallest. You can just mark each element as negative, and then you can solve, you can apply the same algorithm and you will be all okay. But because there are zeros as well, so zeros are neither negative nor positive, you will hit some roadblocks whenever there are zeros. So that's where like what I have done, like there are again multiple possible solution, but what is one possible solution, what I have done is, let's say we have given this array. So what I have done is sorted the array. So this is the sorted array, and take the sum of all positive integers. So this is the largest sum, right? This is the largest sum that you can get. So here it is 20, 12 plus 4 plus 3 plus 1, which is 20. Now once you have found out the largest sum, everything after this would be smaller than 20, right? You need to find the kth largest, right? So everything smaller than this, everything after this would be smaller than 20. So in a way, what you can say is, uh, whenever you are sorting it in descending order, the first element would be 20, second element would be 20 minus some x1, okay, third element would be 20 minus some x2, and so on and so forth. Now, what is this x1, x2, x3, x4? This is the number, the thing that you have to subtract. So now, if you consider this thing, you will be subtracting things from 20, and if you remove some of the things from here, you will again be subtracting things from 20. So either way, you will be subtracting things from 20. So what I have done is uh, convert this negative into positive as well. So now if you convert this negative into positive, the new array would become something like this. Now you sort this. Now this array actually denotes, like if you take any subsequence of this array and subtract it with 20, you will be getting all the subsequence of the original array, right? So now, because you are finding out subsequences of this array, and this array is has all the positive elements, and you have to find out the kth largest. Now for kth largest, this x should be as minimum as possible. So in a way, you have to find out kth smallest subsequence of this particular of this particular array, which only contain positive integers. So hope this point also makes sense. Just to reiterate, what we have done, we have found out the largest element, and now after finding out largest element, what we are saying is this is the largest element in our subsequence list. So every value after in our list would look something like 20 minus x of I. Now because everything is like subtracted here, so how, like you have considered this 12, 4, 3 and 1. Now you haven't yet consider minus 2 and 10. So if you consider anything here, like if you add this thing to your set, you will be subtracting things from 20. And similarly, if you remove something from here, again you will be subtracting things from 20. So these two things are now become identical, right? Because whatever you are taking, you will actually be subtracting from 20. So what we have done, we have just removed this like negatives to positives, like we have converted these negatives to positives, and finally we are saying that what is the kth smallest subsequence here. Why smallest? Because we are subtracting these things from 20. So the minimum is small, minimum is subtract, the largest value we will get. So that's why we have to find out the kth smallest kth smallest integer of this particular subsequence. So this is exactly what we have done in both the solution. In the beginning, we have calculated the sum of all the positive integers, and for all the negative integers we have converted it to positive integers, and finally we have sorted the array, because again we have to apply that algorithm whatever we have just discussed in a sorted array. Otherwise, the approach that we have discussed, that okay, so just to reiterate that piece as well, so we have like this approach that we will always take the smallest element. This approach will fail if the array is not sorted. Why? Because if let's say the array is not sorted and there are like there are some elements after this which is smaller, so you will not be expanding afterwards, right? Because let's say you will, we have stopped at 2 comma 2, right? Why? But if they, let's say there is some element which is smaller than 2, let's say minus 5, again this is just hypothetical because minus would not come here, but for example, let's say minus 5 was there after this. So because we have stopped here, we will not be encountering minus 5 at all. So that's where we need to apply this algorithm on a sorted array. So hope this entire solution now makes sense. If you have any doubts in the question, please post them in the comment section below. I will be happy to answer. Uh, I would strongly encourage you to rewatch the sections that you don't understand, and I'm pretty sure that you will get the solution because I've tried to break it into multiple pieces. And finally, I have taken this approach from one of the Stack Overflow question. Uh, I will post the link in the description below. So this is the question that I have referred uh, in the live contest, but as I mentioned, I haven't submitted the problem because I was not able to solve it myself. So hope you enjoy it. If you like the video, give it a thumbs up. Do subscribe to the channel if you haven't already. Thank you.